Yes, it was fun. All right, I will begin with a word of prayer. So let me see what time I'm starting. Oh, 4:30. All right, good. Dear Father, we thank you for this day again. I thank you for this class and the opportunity we have to meet and study your creation. Guide our steps today. Help us to understand the calculations and bring us to a deeper understanding of the material. Lord, in your name I pray, Lord Jesus. Amen. So this is lecture 12, which is on the multipole expansion. And I feel like I have some kind of sort of heuristic explanation for what this is. And so once we get to it, I'll tell you that, but I'm going to get into it first. So multipole expansion. And so the story begins, well, let me tell you the end at the beginning. So the big picture here is that we can take a charge distribution, right, and the potential due to a charge distribution, and we can write it as if it was arising from a monopole and a dipole, a quadrupole, an octupole, and so forth and so on, whatever those are, all at the origin. If we choose the strength of the monopole, the strength of the dipole, the strength of the quadrupole, and so forth, if we choose the strengths of those poles and higher poles, the multipoles, appropriately, then we can reproduce any voltage that we get from a given charge distribution. So, to me, this kind of smacks of the idea in mechanics we have where we replace a whole system of particles with a single particle at the center of mass. It's kind of that kind of concept. It's sort of replacing something more complicated with a toy model. I mean, a monopole is very simple. All right, a monopole is just the Coulomb field or the Coulomb potential. A dipole, well, that's the next thing. So we should talk about that because that's not familiar to you guys yet, right? So let's talk about the dipole. What is the dipole? And I'll start by talking about the physical dipole. There's also something called a pure dipole, which is, well, not a physical dipole. But first let's talk about the physical dipole. The picture, what we do is we put like a negative charge here, all right, positive charge up here perhaps, all right. We usually, for the sake of understanding the thing, imagine a line connecting these two, all right? Because in the dipole, they're somehow connected, either through perhaps some sort of molecular situation or something. Anyway, they're situated so that they're a distance d apart, all right? And then what we want to do is we want to explain what the voltage is, what the potential is out here at some point, right? And at that point, we can, well, we're going to put, well, just for the sake of specificity, let's put the origin at the middle of the dipole, right here. All right? So we want to calculate the potential out here to the field point. So here's my R, right? And so basically to set up the voltage, to set up the potential here, it's pretty simple, right? There's just 2 point charges. I guess I was supposed to tell you, this is Q, and this is minus Q. So equal but opposite, paired, distance d apart. All right. And all right, so this distance here, that's supposed to be a line, use your imagination. We'll call R plus, and this distance here is R minus, right? And this angle here, theta, well, we can write out some formulas here, right? So if you look, imagine my straight lines were actually straight. You'd see triangles there, right? So we can use the law of cosines. And so like this distance here is what? D over 2, right? So I have like, let's see here, R plus is, you know, d over 2 squared. Oh, I forgot. Sorry, let me put the other one first. So r squared plus d over 2 squared minus 2r d over 2, and what was the angle? Yeah, cosine theta. Is that supposed to be a theta? No, it's a theta. Oh, fine, it's fine. I'm thinking of a later calculation. All right, so that's that. And if that's theta, what's this angle down here? Right, so pi minus theta, right? And so if I do that one, law of cosines, r minus squared is again r squared plus d over 2 squared minus 2r times d over 2 cosine of pi minus theta, right? What is cosine of pi minus theta? So this is cos pi, cos minus theta, you know, minus sine pi, sine of minus theta, right? Also known as minus cosine theta. All right. So we put these together, and what we got is we got r plus minus squared is r squared plus d over 2 quantity squared minus plus. The 2's decanceling, right? So rd cos theta. Are we good so far? Okay, so then for sorry, I wrote too small on my paper. Now it's messing me up. Yeah, I need to, exactly. That's right. I just want to do a little bit more math before I do that. So we're interested in the whole point of this, the whole point of all this discussion is ultimately to find far field approximations to problems. It's not so much about describing the problem close in, it's about what it looks like really far away. All right. So because the dominant contribution to the potential and thus to the field is like the lowest kind of pole which dominates, right? It turns out that if there's a monopole contribution, if you get far enough away, it just looks like the Coulomb field, right? But if that's 0, then the dipole is the leading thing. And if that's 0, then the quadrupole is the leading thing. But ultimately, the application here really is, the thing that's of interest is the case that we have, all right, so factor out an r squared here. And we've got, what, 1 plus d squared over 4r squared, yeah? Minus plus what? D over r cosine theta. You see that? Okay, so if r is like much, much greater than d. In other words, if you're very far away from the particular details of the dipole, right? You're much further away. You're far enough away that you can't really see the distance between the charges, right? You're pretty far away. Then this term here, it's puny, so we don't care about that. So then in that context, this is approximately, you know, r squared times 1 minus plus d over r cosine theta. Right?
Not also diminished? Yeah.
Well, yes, but that's, if we get rid of everything, we're just going to get 0, which is also true. It's pretty small. The field's pretty small away, very far away, but we don't want to go that far. We're just trying to get rid of the thing that's bigger. Excuse me, the thing that's more small. This is second order small. This is just first order small. Okay, in this approximation. So, I hear you. Your complaint has been registered. So look, if we solve for 1 over r plus or minus, what is it? It's like 1 over r, right? And then 1, let's say 1 plus u to the minus 1/2 power, where u is equal to minus plus d over r cosine theta. So what I'm doing is I'm flipping and then taking the square root, all right? R is assumed to be positive, so factor that out, fine. But this, right, like you're telling me is small. U is small. That makes that what I'm about to do not just a good approximation, like it makes it very, very good approximation. See, because I can replace this with 1 minus 1/2 u plus stuff, right? That's the binomial series. Okay, it's just the first two terms in the binomial series, but there it is. But this gives me 1 over r times 1, what we got here? Minus 1/2 minus plus d over r cosine theta, right? Which, all right. So you told me a minute ago, Sam, that I should look at the Coulomb potential, right? So let's do that. It's going to be q over 4 pi, q over 4 pi epsilon naught, right? 1 over script r plus minus 1 over script r minus. Do you guys see that? I bet you thought about that 5 minutes ago, right? Okay. But now we have approximations for that in the far field that we're interested in, you see? So we can rewrite this as q over 4 pi epsilon naught. Well, there's a common 1 over r, right? So I can bring that out. All right, so the 1 over r plus is what? It is 1. So with the plus, I get what? I get a minus d cosine theta over 2r, right? That's my r plus 1. Then I do minus 1 plus d cos theta over 2r. The ones, they be canceling, right? And what we get is q d cos theta divided by 4 pi epsilon naught r squared. But notice that this is voltage. I mean, this is the potential, right? So what was the Coulomb potential? It's like 1 over r, right? But the 1 over r parts canceled out here, right? They cancel out in the far field, and we're just left with, what did I do?
Should it be 8 pi?
No, 1/2 plus 1/2 is 1.
Oh, yeah.
So, yeah.
And how did you get the signs inside of those?
Minus, plus, minus, 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 plus.
But don't those associate, like doesn't the top one associate R plus?
Nope. That's not my notation. Plus goes with plus, minus goes with minus.
Well, wait. Yeah, because it's R plus or minus, you have a minus or plus thing.
Yeah. Well, I don't know. Maybe, am I got it backwards? well, I don't know. If I did that, then I must have made an even number of errors. Where's my other error? I mean, this is the correct formula for the potential for the physical dipole in the far field. So, I don't know. I was trying to be careful. I guess I showed you too many details.
Oh, well, I guess it doesn't matter.
But this is how it works out. So whether or not my notation is Anyway, I'm going to go on. So there are. Let me draw the pictures for you guys. So I've been using these terms, monopole, dipole, so forth. Like, let me give you some silly pictures to kind of hang your hat on. So the monopole is like this. The dipole, of course, is, wait a minute, my color coding is backwards. Monopole, dipole. All right, and I was using a green connecty line. Oh, what in the world? What happened there? This is not a good sign. I don't know. I'm not sure I'm going to survive this lecture here. So this is distance d, right? Now the quadrupole is something like this. You got like minus, minus, plus, and plus. And it doesn't have to be like this, guys. I was looking in the other E&M book, and they have a quadrupole which is not having this geometry. It's just like this is one possible way it could be set up. Yeah, these are planar, I suppose, but not the next. The octupole. I have to cheat and move my picture. So, and then I may have drawn this too high on the board. Oh well. Man, I can't. I'm sorry, I'm wasting your time with these pictures. You'll forgive me. Or not, I guess, but. There's one back there. I'm not sure I can really draw this without. Whee! Octupole. All right, so the monopole, the potential due to a monopole is something like 1 over r. The dipole, the potential goes like 1 over r squared. The quadrupole, the potential goes like 1 over r cubed. The octupole, the potential goes like 1 over r to the 4th when you're far away from it. Now, that's not the full story. It's more complicated than that. There's actually an angular dependence, right? Like the Coulomb potential is spherically symmetric. It's the same in all possible directions. That's already spoiled with the dipole. Do you see that? Like the dipole has got that cosine theta, so it's not the same in all directions. It does have that azimuthal symmetry, right? It's got a phi independence. So if you could picture it, you can rotate that picture around the z-axis if you put the dipole on the z-axis, as we usually do. All right, so let's get to it then. So I want to now derive the multipole expansion for you guys. Multipole expansion. And the starting point is, well, remember our formula for voltage? We have V of R. It's 1 over 4 pi epsilon naught Z integral of what? Rho of R prime d tau prime, right? So we integrate over the charge density And I feel like I'm missing something, right? There's a pesky little term here that we need to take account for, right? This is where it makes it unpleasant. The script r here is what makes this integral like a pain to actually calculate, right? We've experienced this. And so, all right, well, let me try to picture what's going on here. So here's the blarb. My charge is down here, all right? And for the sake of visualization, we'll put the origin within the blob. It doesn't have to be, but whatever. Put it there. I want to think about a wee bitty d tau prime, all right, where my little bit of charge is. And then I'm setting up my r prime, right? I want to find the potential out here at my field point, r, right? And you know the deal. Script r is this distance right here, right? Use your imagination, that was supposed to be a straight line. All right? Now, we're going to call this angle down here alpha. Okay? And what I want to do is I want to look at that triangle. So you guys tell me how this works. We've got script r squared. Let me write a different color here. Script r squared equals to what? It's equal to like r squared plus r prime squared, right? Log cosines, what else? What else we got here? Yeah, minus 2 r prime cosine alpha. So what Griffiths does at this point is he factors out an r squared. And you can kind of appreciate why he's doing this in terms of our previous example. Oh. Example 1. I think that's example 1. Yeah, that may be my only example today. But mostly I'm introducing terminology for you guys today. But so we have r squared plus r prime squared minus 2r prime cosine theta. So if we factor an r squared out of this, what happens is we've got a 1 plus r prime over r, quantity squared, yeah? And then minus 2 r prime over r cosine alpha, right? Everybody agree? I hope. And so at this point, he introduces a sort of simplifying notation, which is he lets epsilon be the following. It's going to be r prime over r times r prime over r minus 2 cos alpha. So with that notation, do you see what happens in the thing above? What is this then? Like this, yeah, it's 1 plus epsilon, right? So then if I want to solve for r, script r rather, script r is unscript r times the square root of 1 plus epsilon. All right. And so we don't face script r in the formula for the potential. We face 1 over script r. right? So let's work on that. 1 over script r is equal to 1 over r times 1 plus epsilon to the minus 1/2 power. But you guys know the binomial series, right? Well, you're going to learn it today. So this is 1 over r times 1 minus 1/2 epsilon plus 3/8 epsilon squared minus 5/16 epsilon cubed plus dot 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 dot. There you go. Those are like the first 4 non-trivial terms in the binomial series, right? You know who knew the binomial series? It's a good part of how he did calculations. What's that?
Griffith?
Newton. Yeah, Newton. But yeah, Griffiths also. Fair enough. Let's credit where credit's due. I mean, he did write the book, right? But what's that?
I know the binomial series too.
Shane knows the binomial series too? Oh, okay. Well, that's a fair point. A fair point. All right. So let me just let's just muse on this 1 over script r here for a bit. All right. Let's take our time. Write this out. And you guys, once I write that out, I want you to see if it looks like anything you know. Here we go. So there's a 1 over r that just stays out front. So we'll just leave that out there, minding its own business. All right? It's there, though. 1, that's easy. Next, minus 1/2 epsilon. What was epsilon? That was that.
Yeah.
So r prime over r times r prime over r minus 2 a cosine of alpha. Well, we have now reached the minus 1/2 epsilon stage. Now to the 3/8 epsilon squared. So here we go. Plus 3/8 epsilon squared. Now epsilon squared oh yeah. Thank you. R prime, I lost my way. Yes, r prime over r squared, and then what? Oh, then r prime over r minus 2 cosine alpha quantity squared. I won't try to do it all at once. I'll just write it. Okay. There we go. Now we've reached the 3/8. What's next?
Minus 5/16.
Minus 5/16. And we've got ourselves a r prime over r to the power 3. R prime over r minus 2 cosine alpha cubed. And this goes on. All right? Now, if you're just glancing through the chapter and you see this, it's very scary to see. It seems like this is a hopeless endeavor. But let's go on. Something amazing happens here. This is 1 over r. 1 minus r prime over r cos alpha plus r prime over. So what we're going to do is group things in terms of these guys, right? The r prime over r term, the r prime over r squared term. So as you can see, there's only this 1/2 times that 2. Minus minus gives me a plus. That's where I'm getting that from. Do you guys see that? Like this times that gives me this term, all right? And there's no other way to get a single r prime over r factor. So next up, r prime over r squared, what goes there? We got this one, right? That gives me a minus 1/2. Is there any others?
Yeah. 3/8 r prime over r squared.
But that always comes with either a cosine alpha. There's no constant. Like I think the only thing is if I'm not missing something. Well, let me just let me cheat here. So I think I've got a minus 1/2 here, right? from this term. And then what did you say for cosine alpha? So there's no, this is done now, right? This is done. It's all in here. All right. So now we're over here. And yes, we've got a what do you say, 6/8?
Should be 12 feet.
Oh, I got to square this though, right? Be careful. This squares to what? You know, r prime over r squared minus 4 r prime over r cosine alpha plus 4 cosine squared. That's this piece becomes all that. So you're what are you saying? We're looking for the r prime over r squared. So that's this term, right? So that's 12. I can't. I think it's 12/8.
Yeah, 12 feet.
Cosine squared alpha. And I think that's the only way we can get just a square there. Let me double check that. So it's supposed to work out to 3 cosine squared alpha minus 1 over 2. Is this 3/2? That is 3/2, isn't it? All right. This is 12 over 8 is 3/2.
Yeah.
Okay, so it's harder when you're closer to the board. It's easier for you guys. You're all the way over back there. Don't make fun of me. It's not nice. So this is, 3 cosine squared alpha minus 1 over 2, all right, plus stuff. Yeah, exactly. These are Legendre polynomials. This is 1 over r, p0 of cosine alpha, plus, I think that was supposed to be a plus. This was a plus, guys. Look, because minus and minus is a plus. I said it, but then I wrote minus. But this is decidedly a plus, okay? So plus r prime over r, p1 of cos alpha, r prime over r squared, p2 of cos alpha. And if we had actually worked out the next one, we would have gotten r prime over r cubed, p3 cosine alpha, and so forth. Notice that I am not making any far field approximation here. This is an exact calculation. And so, like, generally speaking, we get the following beautiful result, that the voltage, the potential rather, at R is 1 over 4 pi epsilon naught. The sum n equals 0 to infinity of 1 over r to the n plus 1, the integral of r prime to the power n, the nth Legendre polynomial at cosine alpha, times the charge density at r prime, d tau prime. And this right here, guys, is the multipole expansion. If you write this out more explicitly, what you got to start with is like 1 over 4 pi epsilon naught q over r, and then plus plus stuff. Now here the q is simply the integral of, rho of r prime d tau prime. My energy is waning. If you guys don't mind, I'm going to use the projector here for a bit. We made it through the really interesting part, at least. So, yeah, but so what this is, once we unwrap it further here, like the 0th contribution is the monopole. Like the next one up is the dipole. The next one past that's the quadrupole, and so forth. And they're found by doing these particular integrals. I mean, now no one really does these integrals, right? Like that's not the point. The point is that we have an approximation scheme for the potential in terms of which is the most dominant term far away, right? And this is used a fair amount in the very later chapters where you're trying to analyze like radiation fields and things. So it actually does matter to us towards the very end of the course. I don't think this is going to help us even a little bit in like chapter 4 or chapter 5. Well, okay, chapter 4 maybe a little bit because we talk about dipoles in like matter next week. So it may matter a little bit next week, but I think like largely speaking, I don't ever remember in my undergraduate course, guys, like, oh, top hat. That's an idea. Let's do that.
You can do it a few times to make up for the last.
If you do a few times to make up. Well, at least you guys are here. How does 8231 sound to you? That's good, because that's where we're at. That's where we're at. All right. So we actually, in class today, we've added a little bit more detail here than I have in the notes, like that theta, pi minus theta thing. I had not appreciated until you guys helped me work it out. Although now you've made me doubt my signs, so thanks for that. But this is right. It's just right. Anyway. So yeah, here it is in its glory. And if you write out explicitly the formulas here for say n equals 2, 0, 1, 2, I think, those are respectively the monopole term, the dipole term, and the much less familiar quadrupole term. This, you can see that this is straight up the Coulomb piece, right? Like it's just, this is charge divided by, distance from the origin. That's the monopole part. The issue here is we're not talking about a charge at the origin. Understand, we're talking about possibly a charge that's distributed over some region, all right? And anyway. So here's the definitions. The monopole piece is just Q over R, where Q is the total charge of the distribution. The dipole piece actually is P dot R hat divided by R squared. Now here P is the dipole moment of the distribution. That is formally defined to be the integral over the distribution of R prime, like this. That's the dipole moment of the distribution. Now in the continuous case, which is often where we'll actually work problems in here, we'll just calculate the dipole moment of a finite collection of charge. So there you don't need to do integration. It just becomes the weighted, like the charge weighted sum, right? The charge sum, what's this called? I don't know. But we use the charge as weights, and this is the position vectors of the charge, and that's the dipole moment for a system of like n charges. But the continuous, come on, don't die me now. You have one job. All right. The continuous extension of this is that, right? You turn this integration, if you turn this summation into an integration, you get that. But the funny thing is here, we went the other way, right? We started with the integration, and we got to this because we've derived the concept of dipole moment for the multipole from like a continuous distribution of charge over there, So it's kind of a funny thing, I thought, but. Now a physical dipole, like we did at the start of class, example 1, it's just, two charges, a plus and a minus, separated by a distance d. And there, the dipole moment is literally just QD, where D is the direction vector from the minus to the plus. Right? That's the dipole moment of a physical dipole. But the ideal dipole has the distance between those charges going to 0, while the charge is going to infinity in such a way that the product of the charge and the distance between the charges is held fixed at P. This is the weirdness of the
That's,
perfect dipole.
that should really be the ideal dipole, right?
This is the physical dipole. The ideal dipole has D 0.
Which is where you get that QD kiss at the
That is true. That is the thing. Is very good. The far field approximation for the physical dipole is the ideal dipole, because very far away from a physical dipole, it becomes the ideal dipole field. Now, I made a copy, a couple things for you guys. So this is Lorraine and Corson, which is another book I have, which is, I thought about using this book. And so this, on the cover of the book is a picture of something. I'm not sure what this is, actually, now that I think about it. But it's one of these things we're talking about. You guys see if you can, I don't know, you guys can figure it out maybe. I'm not sure what that is, if that's a, maybe that's not the, that might actually be the, that might be the quadrupole actually, right? Now on the back of this, I made a, I don't know if that's even show up on the camera, but anyway, on the back of it, I actually, so we were trying to draw this picture in the last class, Sam, right? And like here is actually the honest to goodness picture in figure 422. Next week, we'll cover the one in the bottom. So next week, we'll talk about insulators where the electric field lines can go inside. It's not like that's the next chapter in the story. It's like matter. What do you do with matter, right?
This is actually a dipole.
Is it?
This is the equipotential in the field lines.
Oh, it has equipotential on the field lines, but you think it's a dipole? I don't know. I have to think about it, but so here's the deal, guys. Some comments that we should, think about together. A point charge Q at the origin is a pure monopole. However, if you move it away from like, even if we just had one charge, right? If that one charge is not at the origin, it has a multipole expansion. It has an unending multipole expansion. Because that infinite series over there, it just goes and goes, even for a single charge, if it's not at the origin. See, the multipole expansion is the ideal. The way it works is you're thinking about the monopole and the dipole and the quadrupole and the octupole. They're all at the origin. So if your charge isn't at the origin, it's weird. You're trying to describe a charge not at the origin as if it's at the origin. In order to do that, you have to like add in monopole, dipole, quadrupole, all this stuff. All right, which is weird, but there it is. I mean, that's how it works. So. Nevertheless, the monopole moment is independent of coordinates. That's pretty evident. Like if you shifted the coordinate system, this integral is not going to change, right? If I move the origin, this integral doesn't change. However, the dipole moment is sometimes independent of the choice of origin. See this calculation here? Well, let me scroll down a bit. So like here's the picture. Suppose we had two different coordinate systems, like unbarred and barred. I have to do this funny R bar vector because I don't have a way to bold things. So I just, I wrote this once in a mechanics test and my professor it like offended him to put a bar under the vector or something, or above. I can't remember which one it was. One or the other he found very unphysical. Physicists gained like an idolatrous attachment to notation, honestly. So anyway, let us not make idols of the notation, but do write vectors where they belong, please. But that's like the high places. I won't get rid of them. But I was almost a good king. Oh well. Yeah, with respect to the barred and the unbarred coordinate systems, we can do the integration. Oh, I meant to white that out. I'm sorry. We can do the integration to calculate the dipole moment, right? But the thing is, if you go up and look at the calculation, oh man. the scrolling. I'll eventually learn how to scroll. If you look at the dipole moment in the barred system, in other words, p bar vector, we integrate over r bar vector prime, like that. And I probably owe you like another, don't think too hard about the notation here, but the point is that r bar is actually r prime minus a, and then this integral gives you this integral minus that integral, but this is just q. This is just q, you see. So to calculate the dipole moment in a shifted coordinate system, moving the origin changes the dipole moment, unless the net charge of the distribution is 0. If the net distribution charge is 0, the net total charge of the distribution is 0, then the dipole moment is invariant up to a shift of the origin. All right, which is kind of neat.
No Q being 0, for instance, if you had like a positive and a minus at the same value.
Right. Yeah, like for example, if our distribution is just the physical dipole, the dipole is independent of your choice of origin. But if the net charge was not 0, that's not the case. Moving your origin will change the dipole. This is probably somewhat like the story of torque. You know, torque depends on your choice of pivot point, you know. So, so then finally, we've just been talking about potential, you know. But what about the electric field for the dipole? For the pure dipole, actually. All right. Well, the voltage, the potential is given right there, p cosine theta over 4 pi epsilon naught r squared. If we put it along the z direction, like this, all right, then take the representative, you know, spherical gradient calculation, partial v partial r, and we need these multiplying factors because it's a spherical gradient, right? Well, there's no phi dependence, right? So I guess in that sense, it's not too surprising to see the Legendre polynomials pop up. You know, this is kind of their domain. But anyway, like that weirded me out. I was just like, wait, what? Cool. Anyway, but these are this and that. So there you go. That's the electric field for the dipole. And so here's a picture, my attempt at a picture of the electric field for a physical dipole versus the electric field for a pure dipole. And the thing is, if we could get very far away, they'd actually look the same. The other very neat homework problem, I don't think I assigned this to you guys, but I meant to work it out in class, but I guess I'm probably not going to have time. But if you you can rewrite the formula for the dipole in a coordinate invariant way, just like this, where p is like p vector points from the negative to the positive charge, and you know, this r vector points radially away from the origin. This is a formula for the electric field relative to just the dipole vector and the radial vector out from the origin. This is sometimes a handy formula to know about if you don't want to, if you have a dipole which is not in the z direction, but you still need to find formulas. Like this is helpful. I remember using this one in my course. Okay, that's why I'm mentioning. But yeah, let me see if I can find something. I have some pictures that kind of illustrate the whole idea of dipole moment and the multipole expansion. If I can find, I made these pictures for Physics 232 years and years ago. Because, you know, you should obviously cover the multipole expansion in Physics 232. I didn't really do that. It's a lie, don't worry. Even I'm not that crazy. Here we go. So back when I had enough patience to make Mathematica do stuff for me, I made this. So what this is I make the, so I had a, this is my Coulomb field. It's like the electric field, it's what is this? This is like r divided by r cubed, basically, all right? It's r divided by r cubed is what that is, and that one puts it at the origin, I think. Although in my my picture down here, you notice what I did? I put it at 1, 1. All right, so I put the charge at 1, 1. That's what it looks like. There you go. That's the Coulomb field. You know what? You love it. There it is. Now this is a stream plot from Mathematica, which means it doesn't obey the laws of physics streamlines, which is we only draw lines starting where there's charge. If you look at this picture, you'll see Mathematica every so often starts lines where there's no charge, because Mathematica is very bad at physics. Here is a picture of a negative charge. Hey, the field lines go into it. All right, nothing too surprising yet. 2-point charges. So here I put a charge of positive, these are both positive charges, right? So that's what it looks like if you're close in, right? They're going away. The fields kind of bend when they get in the middle, and the field lines can't cross, of course, right? And then, okay, what happens if you zoom out, though? If you take that picture, so that's at a picture at a scale of plus or minus 3, here's the same charge distribution at a picture of plus or minus 30. What does it look like?
One charge.
One charge, right? That is the fact that this charge distribution is dominated by the monopole field, because it has a net charge that's positive. Going on here, this is what am I doing here? I've got one negative, one positive charge, exactly equal. This is the dipole field from having one at 1, 1, and other one at minus 1, minus 1. Right? What happens if I zoom out? If I scale, go out to 30, look, it's the pure dipole if we look at far away. See that? All right, that's the dipole field. Now what happens if I make the positive charge 1% bigger than the negative charge? Close in, still looks like a physical dipole, doesn't it? But when you go out, still looks like a physical dipole. But when you go further out, monopole. Because the net charge is 0.01 charge. So eventually, if you get far enough out, the monopole term dominates. And there is it at 30,000. Just straight Coulomb. Right? So, and here's a funkier one. I guess that's what is that? That's the quadrupole. Is that on the cover? Is it quadrupole or is it dipole?
It's a dipole, but
it's a dipole, but it shows the equipotentials. Ooh. Isn't that pretty? Ooh, look at this. I don't even know what that is. What is this? We got 2, minus 1, minus 3. What's the net charge here? I've got minus 5 and plus 4. So if we zoom out, it becomes a what? It should be Coulomb. Minus 1 should be, did I actually do it? Oh man. I decided to go 3D at that point. I guess I got bored. Trash. Look at this trash. Just trash. Trash, trash, trash. Anyway, so if you want, I can post this in Canvas. If you don't care, I won't. Does anyone care? I mean, you've seen it, so you've seen it. So I just won't post it. Anyway, have a good weekend, you guys. Whew, we made it.